Okay, so in today's video, we're gonna start chapter number 5, which is chemical quantities and introduction to chemical reaction. So in this chapter, we're gonna talk about three important concepts. The first one is the mole. So we're gonna talk about what is mole is and how we can use the moles to calculate how many atoms or molecules you have in the matter. The second one, we're going to learn about what is chemical reaction and how we can write a chemical reaction in the form of chemical equation and how to balance it. And the last, we're going to talk about how many types of chemical reaction there are and what are those, and then we try to learn about all those type of chemical reaction. Okay, so before we go to the mole concept, before we understand what is mole in a chemistry, we're gonna figure it out first what is molecular mass and formula mass and how we can calculate these masses from the molecule or from the formula of the compound given. But before we see how we can calculate, we already know about the atomic mass. We already know how to calculate the atomic mass. We can go to the periodic table. You will see a symbol of that particular element. In the periodic table, for example, if I go to a periodic table, if I say hydrogen, you have a symbol of hydrogen, and on the bottom you have the mass of that hydrogen, which is 1.01 AMU, atomic mass unit, right? Or you can say 1.01 gram, right? So this is your atomic mass for hydrogen that you can easily get from the periodic table, and for all the elements that you have in the periodic table, you can get the atomic mass. And what is this atomic mass? This is an average weighted mass for all the isotopes of that particular element that we already discussed on the previous slide or previous chapter. Then we're going to talk about how to calculate the formula of a compound, the formula mass of the compound. Right, so let's go to the next slide and try to calculate these masses and then learn how we can calculate or get these masses. So let's take an example and try to understand how to calculate the molecular mass first, and then we have an example of water in this particular slide. So what is molecular mass? Is the mass of the molecule. And if you remember, what is molecule? Molecule is when two or more atoms combine together, right, to form a compound. So molecule is a combination of two or more atoms. If you see over here, water is a combination of two or more atoms. Here you have two atoms of hydrogen and then one atom of oxygen. So hydrogen atoms are combining together, and we're gonna figure it out what's the molar mass of this water. So how you're gonna get, you have to see how many, you have to take the individual atomic mass and then combine them together. So we have two hydrogen atom in this molecule. We have two hydrogen atom, and each hydrogen atom has a mass of 1.008, and you have two hydrogen atoms, so you multiply by 2 these number 1.08, you will get this mass. And then you have how many atoms of oxygen? 1. So that means you have one atom of oxygen, and each atom of oxygen has an atomic mass of 16 grams or AMU, that is 16, and you have to add them both together, you will get 18.016 AMU, atomic mass unit per molecule. So I can say one molecule of water has a molecular mass of around 18.02 grams, right? So this is how you normally calculate the molecular mass for any molecule, right? So before we go further, just to make sure understand everyone, so or just to make sure that every student know how to calculate the number of atom in the molecule. So if you see this water molecule one more time, you have this subscript, this 2, this is called a subscript, and this subscript normally tells you how many atoms you have in that particular molecule. So this 2 represent you have 2 atoms of hydrogen in a water molecule. And if you see on the oxygen, there is nothing written, there is no number, no subscript is given. That means if nothing is given, nothing is written, that means you have 1 over there. So that means you have 1 atom of oxygen in this entire water molecule, right? So water molecule is made by combining two atoms of oxygen and one atom of two atom of hydrogen and one atom of oxygen. Now let's try to calculate the formula mass of magnesium chloride. So remember this, for any ionic compound we usually don't calculate the molecular mass, we calculate the formula mass. So remember this thing for ionic compound. And we already learned about what are ionic compound when metal and non-metal combine together, right? So magnesium chloride is an ionic compound, so we have to calculate the formula mass for this magnesium chloride. So let's do the same thing. How many magnesium atom you have in here? You have one magnesium atom. It's not written, but so that means one number of atom. How many chlorine you have in this magnesium chloride? 2 atoms of chlorine. And what you need to do, you have to just multiply the atomic mass of individual magnesium and chlorine together. So each atom of a magnesium has a mass of 24.31 and each atom of chlorine has a mass of 35.45. So you have to multiply. You have 2 of chlorine and 1 for magnesium. So this is your masses for magnesium and chlorine together, and then you have to just add them together to get this formula mass for magnesium chloride. So this is how you normally calculate the formula mass. So we'll try some more example on the next slide. Try to understand couple of more example to calculate the molecular mass or a formula mass. So now let's take one more example to calculate the molecular mass for a new molecule, which is a glucose in this particular example, that has the formula of C6H12O6. That means you have 6 atom of carbon, 12 atom of hydrogen and 6 atom of oxygen. So when they combine together, they form a formula for glucose. And then how to get the molecular mass? You have 6 atom of carbon and the mass of each atom of carbon is 12.01 from the periodic table. And for each atom of hydrogen you have the mass of 1.008 and you have 12 hydrogen atoms, so you have to multiply with 1.008. And then you have 6 oxygen atom and the mass of each oxygen atom from the periodic table is around 16.00 atomic mass unit. So when you multiply each of them together and then later add them up, you will get around 180.156 AMU, and then if you convert into after rounding off is around 180.16 AMU per molecule of glucose, or you can say 180.16 AMU, one molecule of glucose. One molecule of glucose is equal to 180.16 AMU. Let's take an example of NaCl. And what is NaCl? NaCl is your ionic compound, so we have to calculate what's the formula mass for this NaCl. Formula mass. So how are we gonna get the formula mass for NaCl? You will see in the molecule over here you have how many atom of sodium in there? 1 atom. And how many atoms of chlorine? 1 atom of chlorine. So you have to combine the atomic mass of sodium and chlorine. So you says sodium has an atomic mass of around 23 grams AMU, and then chlorine has around 35.5 individual atom from the periodic table. So we know we have just 1 atom of both of them to make this NaCl, so you have to just add the masses of these two together. So you will get around 58.5 AMU. So I can say 1 molecule of NaCl is equal to 58.5 AMU, and this is a formula mass of NaCl, not the molecular mass. Remember this thing. So this is how you can calculate from all the example that we did. you can easily calculate the molecular mass as well as the formula mass of the given molecule. Okay, so now let's talk about the concept of mole that we discussed at the beginning of the chapter. What is mole and then what is Avogadro's number? So before we go to the mole, let me ask you this thing. If you have a sample of a matter, let's say any matter, and then if I say what matter is made up of, we have an atom. Right, so matter is made up of atom. If I say, if I have a matter, how many atoms you have in there that make up that matter? So there are enormous amount of atoms that makes up the matter. So it's very difficult to calculate how many atoms you have by simply counting the number of atoms present within the matter. So scientists has come up with a special term called mole. So if we say a mole of any matter or anything is always equal to some one certain number, which we call as 6.022 10 to the power 23. So a mole of anything, if we talk about matter, so it can be atoms. So 1 mole of anything is equal to this big number, 6.022 10 to the power 23 of that particular thing. And then this number we call as a special number called Avogadro's number. So Avogadro's number just tells you how many atoms of that particle or that particular atom present in a matter, right, for every 1 mole of a matter. So just remember this thing. This is the equivalency that we're gonna use later on to solve a couple of the problem in this chapter. So let's take an example one more time. A mole of helium. So helium is an element. This helium is made up of many helium atoms. So if I take a 1 mole of helium, how many atoms you have in there? So by definition, we know 1 mole of anything, in this case of helium, is contains 6.022 10 to the power 23 atoms of helium. That means Avogadro's number of atoms of helium, because this number is your Avogadro's number. Similarly, if I say, because helium is an element, that's why we are talking about atoms, because atoms, element is made up of atoms, right? If I say 1 molecule of glucose, the time I say a mole of a glucose, then how many molecules you have? You have the same number, Avogadro's number of molecules, 6.022 10 to the power 23 molecule of the glucose. Why you have molecules? Why not atom? Because glucose is a compound, is made up of by combination of multiple atoms together. So that's why the simplest unit is molecule. So just remember this thing too. If I say I have, for example, if I give you an example, if I have 1 mole of a carbon dioxide gas, how many molecule of carbon dioxide we have in that particular gas? So I can say I have 6.022 10 to the power 23 molecule of carbon dioxide. Molecules of carbon dioxide. Right. So this is the definition that we need to understand. And the next question is how a scientist normally came up with this number 6.022 10 to the power 23, which is Avogadro's number. So scientists came up with this number, or scientists define this Avogadro's number as the number of carbon atoms in a 12 grams of carbon 12 isotope. So that means how many number of atoms of carbon you have in a 12 grams of carbon 12 isotope. This normally constitutes the Avogadro's number. So let's talk a little bit more about on Avogadro's number. So we can use the Avogadro's number as a conversion factor too. And we already learned what is conversion factor. We already learned in the dimension analysis chapter how you can use a conversion factor, right? So let's take an example. If I say I have a mole of atoms, so how many atoms we have? 6.022 10 to the power 23 atoms. So what this equivalency? This is a type of equivalency. right? If I say I have 1 mole of any atom, that means I know that I have this number of atom. Similarly, if I say I have 1 mole of ions, and what is ions? If you remember, ions can be positive ion, cation, and negative ion, anion. We already talked about this thing in the previous slide too. So if I say I have 1 mole of ions, that means I have this number of ions. Same thing, if I have 1 mole of a molecule, I have this number of molecule. If I have 1 mole of any formula unit, if you remember formula unit, we always take from the ionic compound. That means I have this number of formula unit. Right, so all these things are we can easily use as a conversion factor. For example, let's take an example on the first one. If I say I have 1 mole of NaCl, how many formula unit of NaCl I have? I have 6.022 10 to the power 23 formula unit of erase this thing. So I can say formula unit of NaCl. So I can make this equivalency. Or if I say I have 1 mole of Na plus, what is Na plus? This is the ion, sodium ion. So that means I can say I have 6.022 10 times 10 to the power 23 of sodium plus ions. Right. So this is how we normally use an ions too. Right. So make sure you remember or understand this concept. Now we're gonna learn about how you interconvert between moles and the number of particles. That means if the moles are given, how you can calculate how many particles you have, and if the particles are given, how you can calculate how many moles you have in there. So you have to know the interconversion between moles and number of particles. And then by definition, we already know about this thing. This is the relation between moles and number of any particle. If I say 1 mole of anything, we know we have this number of particle or atom or molecule. Right? So if you see these two boxes, on the right hand side you have the mole, on the left hand side you have the number of particle, and if you see on the in between you have a two-sided arrow, right? One going towards the left, one going towards the right. Right? So that means you can go both ways. Right? If one thing is given, you can easily calculate the second one. If the mole is given, you can calculate the first one. So let's get back again how they are connected. It's connected by this definition: 1 mole equal to 6.022 10 to the power 23, and this is a type of equivalency. They are equal. So if they're equal, I can make a 2 conversion factor. I can say if I have 1 mole of anything, I have this number of particle of that thing. Or if I say I have a number of particles 6.022 10 to the power 23 particle, I can say, oh, I have a 1 mole of that particular thing. Right? So it's both ways. We already learned about this thing in the previous chapter, how to convert an equivalency to a conversion factor. And we're going to use again the same concept to solve a couple of problems. So let's try to go to the next slide and then try to solve a couple of problems based on this concept. Okay, so now let's try to solve this problem that says how many chloride ions is present if you have 0.102 moles of chloride ion. So that means it says how many chloride ion. So what is chloride ion? Cl negative, because chlorine has a negative charge, right? So if I give you a 0.102 moles of chloride ion, how many number of chloride ions you have in there? So we already know the definition. If I have 1 mole of chloride ion, how many number of chloride ions you have? The Avogadro's number of chloride ions. And I can use this equivalency to make a conversion factor. What we need? I need how many chloride ions, the number of chloride ions. So this has to be on the top and this has to be on the bottom. That's why you have this conversion factor. Okay? And then once you have the conversion factor, you can just put the given number in front of it, and then the moles will get cancel it out, and then multiply the two number on the top, and then you will get how many ions you have in that number of moles, right? So I can say if you give me 0.102 moles of chloride ion, that means you are giving me 6.14 times 10 to the power 22 chloride ions, right? Or vice versa. If I give you this number of chloride ion, you should know we are giving you 0.102 moles of chloride ion. So this is how you normally do the problem to convert moles to number of the number of particles, or the number of particles to a mole. So let's try to do one more problem on the same concept that we studied on the previous slide. It says, the problem says a 1 tablespoon of sodium chloride contains this number of formula unit of sodium chloride, right? Sodium chloride is an ionic compound, that's why we are talking about the formula unit. And how many units you have? 5.15 10 to the power 22. And you have multiple question on this problem, and then we'll try to solve each of them separately. So the first problem is asking how many moles of NaCl are in 1 tablespoon. So you already have the number of particles or the number of formula unit given. It says how many moles. The second one, it says, so the first one, what we need to go, we have to go from particles or formula unit to moles. We have to calculate how many moles, right? The second one says how many moles of sodium ions does this correspond to? And the third one, how many moles of chloride ion does this correspond to? Because sodium chloride is an ionic compound, that's why we need to know how many sodium ion. What is sodium ion? Na plus. Chloride ion is Cl negative, right? And we know sodium chloride is NaCl. Na has a +1, chlorine has a -1 in an ionic compound, right? So let's try to solve each of the problems separately. Let's start with the first one. So how are we going to do the first one? How many moles of NaCl? We already know the relation. I can say 1 mole of NaCl is equal to how many formula unit? 6 Avogadro's number of the formula unit, right? 6.02 to 10 to the power 23 a formula unit of NaCl. Formula units. This is an equivalency we already know, and then we have to make a conversion factor. What we need to calculate, we have to calculate the number of moles. So moles has to be on the top, formula unit on the bottom, multiply with your given number, which is 5.15. Formula unit will get cancel it out, then you have to divide these two numbers, you will get this number of moles. So I can say if we have 5.15 10 to the power 22 formula unit, that means I have 0.0855 moles of NaCl, right? So the second part of the question is asking how many moles of sodium ion, only the sodium part, right, the ions, does this correspond to? If I give you this number, how many sodium ions are present? So before we solve this problem, let's get a concept. If you have an NaCl, this is an ionic compound. If you dissociate this NaCl, it will dissociate as Na plus and Cl negative. So how many, if I have one molecule of NaCl, how many atoms of Na and Cl negative you are getting in there? If you start with 1, you're getting 1 individual, right? So similarly, if I have 1 mole of NaCl, how many moles of sodium ions you are getting? 1 mole of sodium ion and 1 mole of chloride ion, right? So because the ratio is 1:1:1, so whatever you started with, you're gonna get the same number of the individual ions, whether it's sodium or chloride ions, right? Okay, so now let's try to get this concept and try to solve the problem that is given on the top. So how many moles of sodium ion? We already know. I can say 1 mole of sodium NaCl can give you 1 mole of Na plus, whatever we learn from here, I can detect this information, right? 1 mole of NaCl is giving you 1 mole of sodium ion, right? And then what we need sodium ion. So sodium ion has to be on the top and 1 mole of sodium chloride on the bottom. Multiply with your given number that we solved on the previous slide. We already know now about how many moles of NaCl you have in this number, right? So we don't have to use this number again. We already have the moles from the previous part A of the problem. So we put that number, moles of NaCl get cancelled, and then you will get 0.0855 moles of sodium ion now, right? So this is how you solve the problem for any ions. Let's do the last part of the problem, part C. How many moles of chloride ion? You're gonna use the same concept that we discussed on the last slide. I can say 1 mole of NaCl contain 1 mole of chloride ion. And why I'm saying, we already discussed on the previous slide, right? And we can make a one conversion factor. We need chloride ion. This has to be on the top. Sodium chloride is on the bottom, and then multiply with the number of moles of sodium chloride that we solved for from the first part A. Then moles of sodium chloride, moles of sodium chloride got cancelled, and then when you multiply both the number, you'll get this same number of chloride ion, 0.0855. And it makes sense. Why? Because you have to have the same number of moles of sodium chloride that you have for sodium ion and chloride ion, because the ratio is 1:1:1 in sodium chloride. But this is how you normally try to solve the problem, based on the moles and the number of particles. So now let's try to do one more problem on the same concept, moles and the number of particles. It says in a normal blood test, the amount of carbon dioxide, which is CO2, in every liter of blood ranged between 0.021 moles and 0.033 moles. How many molecules of carbon dioxide does the lower end of this range correspond to? So it says the lower end. Which one is the lower end? This one is the lower end of the carbon dioxide molecule. So we have to use this number. So basically it's saying, if you have the lower range, which is 0.021 moles of carbon dioxide, how many molecule of carbon dioxide you have in there? So again, we already know the definition of the mole. 1 mole of, I can say 1 mole of carbon dioxide is equal to the Avogadro's number of molecules of carbon dioxide, right? And we have to use this concept, use this equivalency to make a conversion factor. So you have to put 1 mole of carbon dioxide on the bottom, and we need the number of molecules. That's why it has to be on the top. This is molecules of carbon dioxide. So moles of carbon dioxide got cancelled, right? Because we have to use 0.021 at the lower side. Multiply both the number on the top side, numerator, and then you will get this number. So that means if you have 0.021 moles of carbon dioxide, that means how many molecules of carbon dioxide you have in there? 1.3 times power 22. So this is how you solve this kind of problem. Okay, so now let's try to do one more problem. It says the average coffee drinker consume this number of moles of caffeine, and we know coffee has caffeine in there. How many caffeine molecule does the average coffee drinker consume in a day? So that means we have to go from moles to the number of molecules of caffeine. So what is given? We have 0.015 moles of caffeine and by definition I can say, if I have 1 mole of caffeine, how many molecule of caffeine we have if I have 1 mole? So by definition of Avogadro's number, I know I have 6.022 10 to power 23 molecules of caffeine. molecules of caffeine. So moles of caffeine got cancelled. If you multiply both the number on the top, you will get around, this is 0.005 at the beginning. It's not 0.05, it's 0.005 over here, right? So if you multiply both the number on the top, you will get around 9.0 times 10 to the power 20 caffeine molecule. So that means if somebody is drinking 0.0015 moles of caffeine in a day, that means that coffee drinker is taking 9.0 10 to the power 20 caffeine molecule, right? And how many significant number you need in our answer, what we started with, how many significant number you have in the given number 0.0015. You have two significant numbers. Your final answer has to be in two significant number, 9.0. Make sure you cannot use the counting of significant number from the conversion factor. You don't get the significant number from the conversion factor. You always see what is given, right? That's why we are using two significant number. So this is an important concept. Make sure you know this thing. Okay, so let's go to the next slide. So now we're gonna talk about the mole and the molar mass. So till now what we discussed how moles are connected to the number of particle, which is Avogadro's number, that we discussed till now. But the mole also connected to the molar mass of the molar mass of the compound of any element. So first we're gonna talk about what is molar mass, and then we're gonna talk about how the mole is connected or related to the molar mass, right? So the molar mass is the mass of 1 mole of any substance. That means if I have a 1 mole of any substance, the mass of that substance we call as a molar mass. And the important thing is 1 mole, the mass of 1 mole, right? So let's take an example. Molar mass of a couple of elements. We're gonna take some example from the periodic table. So let's take first example as helium. The atomic mass that is given on the periodic table for helium is 4.003 AMU. Then its molar mass is 4.02 grams per mole. So remember this thing. The atomic mass unit given for each element on the periodic table is same as molar mass of that particular element, but the units are different. If you can see, the atomic mass are the unit of AMU, atomic mass unit. The molar mass, even though have the same number, but the units are gram per mole. So that means what this unit tells you, it tells you for every 1 mole of that substance, you will have the mass of that substance given in the periodic table, right? Similarly, carbon has an atomic mass of 12.01 in the periodic table. Then what should be its molar mass? 12.01 grams per mole. So that means I can say if I have 1 mole of carbon, that means I have 12.01 grams of carbon from this definition, grams per mole. Similarly, from the top I can say if I have 1 mole of helium, that means how many grams of helium I have? 4.003 grams of helium. From this definition, right? So this is how you normally calculate the molar mass for any element and from the periodic table. So now on this slide we're going to talk about how to calculate the molar mass for a compound. On the previous slide we talk about the element, right, or single atom, the molar mass. Now we're going to talk about how to calculate the molar mass of a compound. So remember, the molar mass of any compound has the same value as the molecular mass or the formula mass of that particular compound, right? We already know how to calculate the molar mass and formula mass, so we can easily calculate but the only difference is the unit. Let's take an example. What does it mean? Water, H2O. We already calculated the molecular mass of H2O, which is 18.01 atomic mass unit, because we combine the hydrogen and atom together, right? Then the molar mass will be the same, 18.01, but the unit will be grams per mole. So that means I can say if I have 1 mole of water, that means I have 18.01 grams of water. Right. One more example, sodium chloride NaCl has a formula mass we already calculated around for 58.44 atomic mass unit, and then the molar mass will be exactly the same, but the units are different, grams per mole, because this is the definition of the molar mass, how many grams in each mole of that particular substance. So I can say 1 mole of NaCl, that if I have, that means I have 58.44 grams of that NaCl. And from this equivalency I can make a conversion factor, and you can easily solve the problem, right? So let's go to the next slide, and then we'll try to do some problems and then try to understand how we can use this molar mass to solve the numericals. Okay, so before we go to the numerical part or to solve the problem, we have to just understand about this picture or diagram that is given over here that shows the interconverting between moles and mass. So we already know moles and molar mass is connected, and how they are connected from this thing. 1 mole is equal to certain grams of that substance. You can say grams of the substance, right? So we're gonna, so if you have the moles are given, you can easily calculate the mass of that substance. If the mass in grams are given, you can easily calculate how many moles you will have, right, from the definition, right? Okay, so let's go to the next slide and try to solve a couple of problems on this concept. So this problem says how many moles of water in 50 grams of water. So the question is saying if we have 55 grams of water, how many moles of water you have in there in that particular grams. So by definition I know 1 mole of water is equal to 18.01 grams of water, right? This is the rule says. And then from this equivalency I can make 2 conversion factor, and then which conversion factor we have to use to solve this problem. It says how many moles, so moles has to be the top, so this is the conversion factor that we're going to use to solve the problem, and just multiply with your given number. So 55 gram is your given number, this is a conversion factor, grams get cancelled, and you will get 3.1 moles of water. So that means if we have 55 grams, that means I have 3.1 moles of water, or vice versa. If I have 3.1 moles of water, we can easily calculate to 55 grams of water, right? And how many significant number you need to have in your answer, you started with 2, right? And I already told you, you don't need to look for the significant number in the conversion factor, so that means your final answer has to have 2 significant number. Let's try to do this problem on this slide. This says what is the mass of 0.25 moles of copper, Cu, which is copper. So the question say if I give you 0.25 moles of copper, how many grams of copper I'm giving you. So by definition I know 1 mole of copper is equal to 63.55 grams of copper, right? And then I can make 2 conversion factor from this equivalency, but which conversion factor we have to use? The one that has the mass on the top. So I can say 63.55 grams on the top divided by 1 mole of copper, and then copper, moles of copper got cancelled. You multiply both the number on the top, you will get 16 grams of copper. So that means if we have 0.25 moles of copper, that means we have 16 grams of copper. And how many sig fig number? We have 2 sig fig number in here. Your answer has to have 2 sig fig number too. right? So this is how you normally solve the problem from moles to mass in grams. Let's do one more problem on the same concept. It says what's the mass, so that means you'll have to find the answer in grams, right? What's the mass of 0.00150 moles of caffeine in milligram? So that means your answer has to be in milligrams, not in grams. Let me erase this one. Your answer has to be in milligrams, right? Given that the molar mass of the caffeine, so this is the given thing, the molar mass, and from the molar mass what I can get the concept or the equivalency. I can say 1 mole of caffeine contain 194.20 grams of caffeine, right? From this number I can say this thing. But before you use this conversion factor or this equivalent to solve to get the answer, first thing that you need to know this, you have to convert grams to milligrams, because the problem is asking for milligrams. So let's try to solve this problem. So this is your given number, this number of moles of caffeine, and we have to use one conversion factor from this equivalency over here. So we need grams, so grams has to be on the top because we need mass. So this number has to be on the top, 1 mole of caffeine on the bottom, and then moles will cancel, you will get grams, but our answer has to be in milligrams. So that's why we have to go one more step, that convert grams to milligrams. So I know 1000 milligrams is equal to 1 grams. So grams get cancelled, and then multiply everything, your final answer has to be in milligram, because every other unit is already got cancelled except the milligrams. So that means you're gonna get around 291 milligrams of caffeine. And how many significant number? 3 significant number in here, because you started with 3 significant number. So this is how you normally solve this kind of problem. So always make a conversion factor from the molar mass, right? So that you can solve the problem. So now we're gonna learn about how you can convert between the mass and the number of particle. If the amount is given in grams, how many particle you have in that particular grams. So we're gonna see. So till now, whatever the problem we did using a mole. If you remember, if the number of particle is given, we calculated moles. If the moles was given, we calculate the number of particle. In the other problem, we used number of moles to convert into grams. If the grams or mass is given, we convert it to moles, right? We just did this kind of problem before, right? Before this concept. But what if the mass is given? Let's say if the mass is given, and if we ask you how many number of particle you have, or if the number of particle is given, if I ask you how many grams you have in there, now you cannot go directly from number of particle to mass or grams, or mass or grams to number of particle. You have to pass through a mole, right? So mole is a center point. You have to pass through this moles to get to the other part of the solution. So we will have 3 boxes: number of particle, moles, and mass, right? And then how the first 2 boxes are related, number of particle and number of moles, how they are related, we know by definition 1 mole equal to Avogadro's number. So this is the equivalency between the first 2 boxes. And how the other 2 boxes are related, moles and grams, we know 1 mole of anything equal to the molar mass of that particular substance. So we're gonna use this concept to solve any problem that has been asking about mass to number of particle to mass. So we'll see 1 or 2 problem on this and try to understand how we can use this concept that we just learned over here. So let's try to do this problem. The problem is asking how many copper atoms are present in 5 grams of copper. right? So it's asking atoms, right? And then what is given? Mass of the copper is given, right? So let's try to do over here. If the mass is given, what I can get from the mass? I can get the moles of the copper. If I can get the moles of the copper, what I can get? I can get the number of particles. So in this case, particle is what? Atoms, right? Same thing. So I'm going to erase the particles. I can just write atoms in there, right? So we have to use these three, or this path goes from mass to moles to atom. So let's how mass and moles are related. I know by definition 1 mole of anything equal to the molar mass of that thing. So if I say 1 mole of copper, how many grams of copper? 63.55. If you go to the periodic table, it gives you 63.55, right? And what we need to have on, so I can use a conversion factor between the first two boxes over here. I can say 1 mole of copper over 63.55 grams of copper, right? So I already connected the first two boxes. What about the other two boxes, moles and atom? I can say 1 mole of any substance, in this case is copper, is equal to 6.022 10 is power 23 atoms of copper, right? And then what we need? Atoms. So atom has to be on the top. How these two connected? I can say 6.022 10 is power 22 atoms of copper over 1 mole of copper, right? So we already connected both the boxes, or both the last two boxes, moles and atom, and then just multiply these two conversion factor with your given number, which is 5.0 grams of copper. So grams of copper get cancelled, moles of copper get cancelled, and then what's left? Atoms of copper. So this is the same problem that we used on the bottom, right? Grams, 1 mole 63.55, 6.022 10 is power 23 atom over 1 mole, everything get cancelled. And when you multiply both all the number and divide by the given number, you will end up with 4.7 10 is power 22 copper atom. So this is how you normally solve the problem, this kind of problem, right? Let's do one more problem. It says what's the mass? Now you have to calculate the mass, and the what's the mass of 2.5 10 to the power 23 carbon atom. If you have this number of carbon atom, what's the mass of that, all the carbon atom that you have? So let's start again. What is given? Atoms or the particles are given. If this is given, what you can get? Can we get directly the mass? No, you have to go through moles, because atoms are connected to moles, not with the mass, but the mole can be connected to the mass of that particular substance. So how the first two boxes are connected? So let's make this is atom, this is moles, this is mass. How the first two boxes are connected? By definition, I can say 1 mole of carbon, how many atom? 6.022 10 is power 23 atoms of carbon, right? And how the other two boxes are related? Using a conversion factor. So it says mole to mass. I can say whatever you're going to get is always on the top. So I can say 12.011 grams of carbon. That means I have 1 mole of carbon by definition. You have everything, multiply everything with your given number, which is 2.5 times 10 to the power 23 of carbon atom, right? atom of carbon. So atom of carbon got cancelled, moles of carbon got cancelled, multiply, divide, solve these numbers, you end up with 5.0 grams of carbon. So that means if you have this number of atom, you have 5 grams of carbon. Right. And this is the same way they solve it on the slide too. And how many significant number you need to get as the final answer? You started with 2 sig fig number, you should end up with 2 sig fig number. Right. Okay, let's try to do this problem. How many molecules of ibuprofen, that has the formula is already given, C12H18O2, are in 200 milligram of the dose? So it is saying if we are getting 200 milligrams of ibuprofen, how many molecule of ibuprofen I am getting? So that means what is given? Mass of the ibuprofen is given, right? So the boxes is gonna be like this. Mass is given. What I can get the mass from the mass of ibuprofen? I can get the moles. And if I can get the moles, I can get the molecules. Why we are getting molecules, not the atom? Because ibuprofen is a compound. That's why I'm writing molecules instead of atoms, right? So the first thing that we need to know is the mass is always in grams, but the given amount is given in milligrams. So you have to convert milligrams to gram first. So 200 milligrams, how you convert? 1 grams is 1000 milligrams. So milligram get cancelled. Now you have grams. And now how the first two boxes are connected, mass and moles. So I can say 1 mole of ibuprofen equal to molecular mass of that ibuprofen, because you cannot get the mass of ibuprofen from the periodic table. So if this is a compound, you can get the molecular mass or molar mass, right? So how you gonna get the molar mass of ibuprofen? You have to get the same molecular mass. You have 12 carbon atom. Each carbon atom is 12.01 multiplied by 12. Each hydrogen atom is 1.008. You have 18 of them, 18. Then you have 2 oxygen atom, and each oxygen atom is 16 gram, right? Multiply and then add them all together. You will get 94.26 grams per mole, because molar mass has a unit of grams per mole. So I can say 1 mole is equal to 94.26 grams of ibuprofen, right, from this definition. And I can use this as a conversion factor, because we need moles on the top, mass on the bottom, and then the last two boxes are connected by this, right? Molecule has to be on the top because we need molecule, and then moles over here. And we already know this rule: 1 mole of anything is equal to Avogadro's number of molecule. So now arrange this thing in a sequence. Then we already got milligram cancelled, grams cancelled with grams, moles cancelled with moles, and then you left with molecule. And your final answer has to be 6.20 10 to the power 20 molecule. And how many significant number? You need 3 sig fig number to solve this problem, right? So assume you have a decimal at the end, right? So this make is as 3 sig fig number. So that's why you have 6.20 10 is about 20 molecule. So let's try to do one problem as in practice. So if we have 4.76 times 10 to the power 24 molecules of NO2, nitrogen dioxide, how many grams of nitrogen dioxide we have if I have this number of molecules of nitrogen dioxide? And then we have to solve for how many grams. So how are we going to solve this problem? So again you have to see which thing is given. Number of molecule is given, so that means we have to start from the molecules. And if I have the number of molecule, can we get directly the mass of that molecule, basically the grams of the molecule? No, we have to get through the moles first, because there is no relation that directly connect molecules to grams. So this is the moles, and once we get the moles in hand, I can get the mass of that molecule, basically the grams of that molecule, right? So let's say how the first two boxes are connected. I know by definition we need moles, because the arrow is going from molecules to moles, so I have to write moles on the top. I have 1 mole of NO2, nitrogen dioxide, is equal to how many? Avogadro's number of molecule, 6.02 to 10 is power 23 molecules, right, of NO2. And now once we get the moles, how we can get the mass? So by definition I can say, because we are going towards the mass has to be on top, can I say 1 mole of NO2 is equal to 46.01 grams of NO2? Why? Because how you gonna get the molar mass of NO2? Because that's the rule says 1 mole of NO2 is containing how many grams of NO2. So how many atoms of nitrogen you have in this? 1. So each nitrogen atom is 14.01 grams, right, from the periodic table. How many atoms of oxygen you have in this nitrogen dioxide? 2 atoms of oxygen, and each oxygen atom is 16 gram around. So if you add them both, 14.01 gram plus 32.00 gram, so you will end up with 46.01 grams. So this is 1 mole of, I can say 1 mole of nitrogen dioxide is 46.0 grams of NO2. So once you have everything, multiply this number with your given number, 4.76 times 10 is power 24 molecules of NO2. So molecules of NO2 get cancelled, moles of NO2 get cancelled, and you will end up with, when you divide these number, you will end up with 365 grams of NO2. So that means if I have this number of molecules of NO2, I have 365 grams of NO2, right? And you started with 3 sig fig number, your final answer has to have 3 sig fig number. So make sure you remember the number of significant number in your final answer too. Okay, so make sure you practice all the type of problem that we did on the slide, and then make sure you understand like the concept of all the problem that we used on the previous slide. So now let's try to talk about what is chemical equation and what is chemical reaction, right? So before we go to the chemical reaction, so we already talk about the chemical changes, right? What is chemical change? Chemical change is a change that changes the chemical composition of the matter, right? So that means whatever the matter you have in before, after the reaction is done, you will get a different matter, that the chemical composition of that matter is gonna change, that we call as chemical change. And how would we know that there is some kind of changes happening due to some chemical reaction? So you will see change in the color whenever you mix any two substance. If there is any change in the color than the previous color that they had, that means there is something going on, some kind of reaction is going on that is changing the chemical composition of that particular reactant or those substance. If you see a formation of solid, if you see some new solid is forming that was not there before, that means there's some chemical changes happening. If the heat is being produced during the mixing or during the reaction, if there is an evolution of a gas, if you see some bubble is coming out, if you mix, let's say if you mix any two liquid and after mixing you will see some bubble is coming out from after the mixing, that means something is happening, some chemical change is happening in there. And the last not the least is noticeable aroma. You will see some, if you don't see any of these changes during the reaction, you might smell some kind of aroma after the reaction is done, right? If you mix any two liquid, before the liquid you don't have any smell from any of the two liquid, but if you mix the two liquid, after some time you will see some smell is coming out, some aroma is coming out. That means this is the chemical change that happened once you mix those two substance together, right? So there are a couple of proof that you can use to identify whether there is some kind of chemical changes happening or not. But this is not the only proof, but this is mostly the proof that you can see by your naked eye easily, right? Or you can smell it. So let's take this example over here, like formation of a precipitate. Precipitate is kind of solid thing, right? By mixing two solution, potassium iodide and lead nitrate, right? If you can see, if you mix these two solution which was clean before you mix them, but after mixing you will see in this picture over here that a new kind of color is producing, right? The yellow color. So that means something is happening between the two solution, right? Some chemical change is happening because of, or else you wouldn't see these different color appearing, right? So this is one kind of proof that you can use to figure it out whether the chemical reaction is happening or not. So there is also some kind of chemical reaction is also going in, like in our body or in living organism, in the form of metabolic reaction, right? We call as metabolism. And we know what is metabolism: to convert a solid particle or a food into a smaller particle, right? To provide the energy for the body, and how we can use that energy that is being created by the process called metabolism in the form of movement. We can use for a movement, we can use to talk, for breathe, for growth, for reproduction. So all the kind of energy that we are getting from these metabolic reaction, which is a kind of chemical reaction, we can use all this energy in different form to sustain life on earth. So now we're going to talk about the chemical reaction. So in during chemical reaction, two or more substances come together, collide with each other and form a new substance, right? This is kind of chemical change. And we normally write a chemical equation in the chemical reaction in the form of chemical equation. So this is a kind of equation, right? N2O2 gives you NO. So we're going to talk about this equation later on, but right now we're going to just learn about what is chemical reaction. So in chemical reaction, two substances, for example over here, oxygen and nitrogen, come close together, collide with each other, and then what's happening? Once they collide, the bond between the oxygen and nitrogen is going to break. And because to make a new molecule where nitrogen attached with the oxygen, you have to first break the bond between them, or else they won't combine with each other. So the bond is getting broken down over here, and then once it's broken down, now oxygen and nitrogen can attach with each other by forming a new bond. So in chemical reaction, first bond has to be broken, or you can say bond has to break down first to form a new bond, right? New bond formed, right? So this is a chemical reaction, right, where the bond is being broken down and new bond is formed to make a new substance, right? And then one more thing from this chemical reaction is the substance that is colliding with each other to make a new substance. We call those substances are reactant. If you can see over here, so oxygen and nitrogen gas are reactant. They are reacting with each other, right, colliding with each other. and the substance that is being formed as a new substance, we call that as product, right? So we're going to talk about more about these reactant and product, but this is just an idea about the concept. What is reactant, what is product? So in any chemical reaction, wherever the two or more substances combine with each other to form a new substance, they always follow a law of conservation of mass. So remember this thing. So chemical reaction always follow law of conservation of mass. And what is this law of conservation of masses? In all chemical reactions, atoms are neither created nor destroyed. Means you cannot create the atom, you cannot destroy the atom. So whatever atom you use at the beginning, you have to have the same number of atoms at the end of the reaction, right? So that means it says reactant and product are different from each other, but they contain same number of atoms. This is the important line, right? You might start with a different substance containing some kind of atom, and you will end up with a different substance as a product, but the number of atom on both sides before you started with, and you end up with the number of atom of the same atom type has to be equal, right? So what's happening in a chemical reaction? Only the bonds between the atom change, right? There is nothing else. Only the bonds in the reactant side is being broken and the new bond is being formed, but the number of atom and reactant and product has to be equal. For example, let's say if I have H2 plus O2, these are the two substances that is reacting with each other and making H2O, water. So what's this law of conservation of mass says? If you start with how many atom of hydrogen? 2 atom of hydrogen, 2 atom of oxygen. These are the substrate, that's why this constitute the number of atom. How many atoms you have on the other side? 2 and 1 atom of oxygen. So that means you missed 1 oxygen atom in the product, which is not true according to the law of conservation mass. So how many atoms of oxygen you should have in water? 2. But we know the formula for water is H2O, not H2O2. So we're gonna learn about this thing later on, but just right now, just know that this is not possible, right? The number of atom that you started with has to have the same number of atom for that particular element, right? So now let's try to learn about how we can write the chemical equation. So we normally write the chemical reaction in the form of chemical equation, because we have, so chemical equation is nothing, it's just the way of writing how the reaction is going on, right? Which two substances are reacting and what you're getting as a product, right? So we have several important information from a chemical equation that we're going to learn right now. The first one is identify the reactant and product. So chemical equation normally tells you which two substances or more than two substances are reacting, means what are the reactant and which things are being produced once the reaction is done. So that means what are the product. So by looking at the chemical equation, you can easily see which one is a reactant, which one is a product. So this is the information chemical equation can give. So let's take this example. N2 plus O2 gives you 2NO. Which one is a reactant? So N2 and O2, these are two are reacting, right? And what you're getting? NO as a product, right? So we can easily know by looking at the chemical equation. The second one, the chemical equation tells you the physical state. What are the three different type of state we have? Solid, liquid and gas, right? So we can easily, by looking at the chemical equation, you can easily see the reactant and product are in which state right now. So there are three kind of the state: small s for solid, small l for liquid, small g for gas, and then you have a AQ, that's called aqueous, means dissolve in water, aqueous. So if you see in this chemical equation that is given on the top, if you see over here N2G, this is called state. So nitrogen is in a gas phase, oxygen is in a gas phase, and nitrogen monoxide also is in a gas phase. So all these three molecules, whether in reactant and product, are in gas phase. The third information that chemical equation give you is the symbol and formula. So if I say nitrogen is reacting, so nitrogen gives, this chemical equation give you the formula. So nitrogen is N2, I know this is N2, right? And then the reactants or the product are separated by a plus sign. So if you have a plus sign between the two molecules, that means they are separate molecule. So in this top chemical equation N2, nitrogen gas, we know the formula from the equation N2 with a plus sign at the center. That means nitrogen gas is a different molecule, oxygen gas is a difference. They are two reacting with each other, right? They are separate entity, right? The fourth one tells you which one is reactant, which one is product, and the reactant and product are separated by an arrow. So if you see this arrow in the chemical equation, that tells you where the reaction is going on, right? In which direction. Basically this gives you the direction of the reaction. So right now we can say the direction of the reaction is towards the right hand side. That means N2 and O2 are reacting to make a product, right? NO. And then last not the least is the whole number coefficient indicated relative proportion. So the important thing over here that you need to know is the coefficient, the number written in the front of this molecules, whether in reactant or product side, we call this number as coefficient. So if nothing is written in front of the molecule, we know this is 1. So nothing is written in front of the N2, but the coefficient is 1. For O2, nothing is written, I know coefficient is 1. And then for NO, the coefficient is already filled, which is 2. That means you have coefficient of 2. So coefficient normally tells you the relative proportion. That means if I use one molecule of N2 gas react with one molecule of oxygen gas, I can get 2 molecules of nitrogen monoxide gas. So this will give you the relative proportion, what's the ratio, right? So make sure you know this thing. And this ratio coefficient sometime also tells you about the moles. So coefficient also we sometimes use as moles. So right now just remember this thing. We're gonna use this term or this concept later in the chapter, where we're gonna talk about the number of moles, right? Right, so let's take this example again that we used in the previous slide. N2 plus O2 gives you 2 NO. So like I said, coefficient represent ratio of reactant and component, right? So the first information the coefficient can give you is the ratio of individual units. So I can say 1 nitrogen molecule, because this is 1, nothing is written, this is 1. It tells you 1 molecule of nitrogen react with 1 molecule to give you 2 molecule of nitrogen monoxide. So this is one of the information that you can get sometime. Like I told you, it give you the molar ratio, the ratio of the moles. So I can say also say from this chemical reaction that 1 mole of nitrogen gas react with 1 mole, because the coefficient is 1 mole of oxygen gas to get 2 moles of nitrogen monoxide. So the coefficient is also tells you the mole ratio. So this is the important thing. Make sure you remember this thing that we're gonna use in multiple problem to solve it. Okay, so let's try to solve this problem. The chemical equation of any of the chemical reaction is already given for you, where the 2 reactant are combining together to give 2 product right after the arrow. So identify the reactant and product. You have to tell me first this thing that we're going to talk about. Identify the coefficient and explain what they signify in terms of molar ratio. And the third one is identify the physical state for each of them, product as well as reactant. And then at the last you have to tell me how many carbon, hydrogen and oxygen atom you have on each side of the arrow and what does it indicate, right? So let's try to solve each individual problem separately, and then let's try to learn how to solve this kind of problem. So the first problem was asking identify the reactant and product. So we know This is your reactant, CH3H8 and O2, right? Which one is your product? CO2 is your product, water is your product after the arrow, right? So this is how you can tell which one is reactant and which one is product. The second part of the problem was asking identify the coefficient and explain what they signify in terms of molar ratio. So what's the coefficient of C3H8? Nothing is written, that means 1. Oxygen is 5, coefficient is 5, carbon dioxide has a coefficient of 3, water has a coefficient of 4. So these integer or whole number 1, 5, 3, 4 are coefficient, and we know this coefficient also tells you about the molar ratio. So I can say 1 mole of C3H8 react with 5 moles of oxygen to give you 3 moles of carbon dioxide and 4 moles of water, right? So these are moles. Now the third problem was asking identify the physical state of each product and reactant. So the time we see it, small g, G is written, that means all the product and reactants are in gas phase or in gas state, right? So this is how you normally get the physical state of the reactant as well as the product. And the last problem was asking about how many atoms of carbon, hydrogen and oxygen you have on each side of the arrow. So let's talk about before the arrow. How many carbon? Let's talk about one at a time. How you have carbon? How many carbon atom? 3 carbon atom. Is there any more carbon on before the arrow? No, we don't have it. So we have 3 carbon atom in the reactant side. How many hydrogen atom before the arrow in the reactant side? 8. There is no one before the arrow, so just 8. How many oxygen? So you have 2 atom of oxygen, but how many atom together? So you have to multiply this number, which is a subscript, with the coefficient. So you have 10 atoms of oxygen, right? So make sure you know how to get the number of atoms for each elements, right? Let's talk about the product side after the arrow. How many carbon you have on the product side? You have 1 carbon atom, because nothing is written, that means you have 1. And then how many total carbon atom? 1 times 3. You always multiply with the coefficient of that molecule, so you have 3. How many oxygen? 2 oxygen atom, but 3 is this 3 coefficient is for the entire molecule, so you have to multiply 2 with 3, 6, right? So you have 6 oxygen atom, right? Then how many hydrogen atom in the second molecule? You have 2 atom of hydrogen, multiply by 4, you get 8 hydrogen atom. And then you have 1 more oxygen, 1 times 4, 4 oxygen. So you have 6 oxygen from one of the product, 4 oxygen from the second product. When you add them both, you will get 10 oxygen. So this is your 10, right? So you have 10 oxygen all together, combining from different product on the product side, right? So this is how you can calculate the number of individual atom on reactant as well as the product side. So now we'll talk about the balanced chemical equation. So whenever you write a chemical reaction in the form of a chemical equation, make sure you always follow the law of conservation of mass. That means reactant and product must contain the same number of each type of atom, and we know atom has some mass. So that means if you have the same number of atom on each side of the chemical equation, that means you have to have the same kind of mass, right? So for example, if you have H2 plus O2 again gives you water. So we learned in the previous slide that you have 2 hydrogen in the reactant, you have 2 hydrogen in the product, you have 2 oxygen in the reactant side, but you have only 1 oxygen on the product side, which is not true according to the law of conservation of mass, because each atom has some kind of mass, right? So you started with 2 oxygen atom, there is no way you can end up with one oxygen atom. That means you are saying that one oxygen atom is already gone, right? And we don't know. And if he is already gone, you will have some mass deficiency in the product side, because you have one oxygen atom less, and each atom has some kind of mass. So this is not true according to a law of conservation of mass, right? So how you going to correct this when we know oxygen atom is not went anywhere, is still in there? So we have to balance this chemical equation. H2 plus O2 gives you H2O, and we're gonna learn how to balance this chemical equation later on, right? So what is balancing of chemical equation? Balancing of chemical equation means to contain the smallest whole number coefficient so that the number of atom on each side of the reactant and product become equal, right? Okay, so let's try to solve this balancing of chemical equation. Let's try to understand on the next slide how you can balance the number of atom on each side. So let's take an example of combustion of methane CH4. Whenever we talk about the combustion, means you are using oxygen atom or oxygen molecule to react with CH4. So when you react CH4 with oxygen, you get two products, carbon dioxide and water. And if you see, you have a coefficient of 1 with CH4 methane, coefficient of 2 with oxygen molecule, coefficient of 1 with carbon dioxide, and coefficient of 2 with water molecule. And then let's see if you have the same number of atom on both sides for each individual same type of atom, right? So let's take how many carbon atom you have in the reactant side. You have just one carbon atom, right? How many hydrogen atom you have on the reactant side? You have 4, because there is no one in the oxygen. How many oxygen atom you have on the reactant side? You have 2 atom. You have to multiply with the coefficient, that means you have 4. Now let's go to the product side. How many carbon atom you have on the product side? 1 again. How many hydrogen? Let's talk about the hydrogen first. 2 atom, multiply by coefficient, that means hydrogen is 4. How many oxygen? You have 2 oxygen atom in the carbon dioxide and 2 oxygen atom in the water, because we have 1 multiply by 2 in the coefficient, you get 2, and 2 from here. So 2 plus 2, you have 4 oxygen atom. So if you see in the reactant side, you have the same number of hydrogen, oxygen and carbon atom as you have in the product side. So that means law of conservation of mass exists in this chemical reaction. So that means the chemical reaction or equation are balanced. You have the same number of each type of atom on both sides of the arrow, in reactant as well as product. So this equation we call as balance equation. And then we're gonna learn how you can do a balance equation if the equation given to you is not balanced. So you have to do a balancing of chemical reaction by yourself. We're gonna learn about this balancing later on. Let's take one more example of law of conservation of mass. This is a chemical equation for glucose react with oxygen, gives you carbon dioxide and water. So the coefficient is already provided, so that means this equation are balanced. But let's confirm whether this equation are balanced or not. You have how many carbon? You have 6 carbon. How many hydrogen you have in there? You have 12 hydrogen in here. And how many oxygen? 6 oxygen from glucose and 12 oxygen from oxygen molecule. So you have total of 18 oxygen atom. Right. Let's talk about in the product side. How many carbon atom in the product side? 6. You have 6 carbon. Okay, balance. How many oxygen? You have 6 times 2, 12 oxygen, and then 6 by 1, 6 oxygen. Total is 18 oxygen. Same. Let's talk about the hydrogen. You have 12 hydrogen. 2 times 6, 12. So that means you have 12 hydrogen. So every type of atom are equal on both sides of the arrow. So that means this equation is balanced, and this follow law of conservation of mass. So let's try to do some balancing of a chemical equation. So this equation is given to you, and if you can see this equation is not balanced, means you don't have that same number of atom of the same type on both sides of the arrow. If you can see from here, you have 6 carbon, you have just 1 carbon atom, right? So this equation is not balanced. You have to do a balancing. So let's try to learn how to do the balancing of a chemical reaction. So the first thing is you have to use one atom at a time, right? Pick one atom and try to balance that atom first. So I'll start with carbon. How many carbon atom you have on before the arrow? You have 6 carbon. There is no carbon in oxygen, so that means total of 6 carbon. And then how many carbon on the product side? You have just 1. There is no carbon in there, right? So how you going to convert this 1 carbon into a 6 carbon? Because we started with 6, we should end with 6. So don't write a subscript 6 in here. Just remember this. You can increase or decrease the number of atom by increasing or decreasing the coefficient number only, but not by changing the subscript. Don't change the subscript when you balancing the chemical equation. Okay, so now let's try to do this problem. We need 6. Put 6 in the front. So this means now you have 6 carbon atom, right? So carbons are balanced. Now you have 6. Let's talk about hydrogen. How many hydrogen you have on the reactant side? 14. There is no hydrogen in the oxygen, so you have total of 14 hydrogen. How many hydrogen on the product side after the arrow? You have just 2 hydrogen. How you gonna make it into 14? Put 7 in the front. To 2 times 7, 14 hydrogen. So now hydrogen is also balanced. So now we have to just balance oxygen. If the oxygen is balanced, everything is good. So how many oxygen atom on the reactant side? 2 oxygen atom, right? There is no oxygen in C6H4, so total is 2. How many oxygen on the reactant side, product side? You have 6 times 12, so that means 12 oxygen from first product, and 1 times 7, 7 oxygen from the second product. So total of 19 oxygen you have on the product side. So how you gonna convert this 2 oxygen atom into a 19? So we're gonna use a concept called a decimal method. So we have to put a decimal number such a way that you can equate the number of atom on both sides. So you have 2 atom in here. What number I should write in the coefficient so that it become 19? Can I write 9.5? So 9.5 times 2 is 19, and then this become equal, right? So this is the chemical equation, right? Balance, but the thing that you cannot tell this is a balance. The important thing is you cannot have a decimal number in a balanced chemical equation. You cannot leave the chemical equation when you have a decimal in there, because atoms cannot be in fraction or in decimal. Atom is a whole number, so you cannot put 9.5 oxygen atom. So but we have 9.5. How you gonna convert into a whole number? 1 2 3 4 5. Multiply the entire number by any whole number or any integer that convert this decimal into a whole number. So the smallest number that we can think of is 2. If I multiply entire reaction with 2, this 9.5 become 19. So this convert into a whole number, right? So let's do this one. So before, let's remove this thing. Okay, so let's try to do over here. So 2 you multiply with the coefficient. This is 1. So 2 times 1, this become 2. 2 times 9.5, this become 19 instead of 9.5. 2 times 6, this become 12, and 2 times 7, 14, right? So the final balancing of chemical equation is 2C6H14 plus 19 oxygen gives you 12 carbon dioxide, gives you 14 water. And if you compare to see now if each atom is balanced, you have 12 carbon atom, you have 12 carbon atom in the product side, you have 14 times 2, 18 hydrogen. Let's say how many hydrogen you have, 2 times 14, 18 hydrogen on this side. Let's say how many oxygen you have in there, 38, right? And then how many oxygen on the product side after that, 2 times 12, 24 oxygen, and then 14 times 1, 14 oxygen. So total of 38 oxygen. So now each and every types of atom are equal on both sides, reactant and product side. So this is a balanced chemical equation now, right? So we always use a decimal part if we cannot get the balancing of chemical equation with a whole number. So this is kind of trick that you can use to balance the chemical equation. Let's try to balance this chemical equation, right? You have 6 carbon on the reactant side, you have just 1, put 6 over here. Now let's balance hydrogen. You have 12 hydrogen on the reactant side, you have 2 hydrogen on the product side, put 6 on the in the front coefficient. So now you have 12 hydrogen. So we balance carbon and hydrogen. Let's try to balance oxygen. You have 2 oxygen from here and 2 oxygen from here. So we have total of 4 oxygen on the reactant side. How many oxygen on the product side? 6 times 12, 12 oxygen. 1 times 6, 6 oxygen. So we have total of 18 oxygen. So we have to just try how balance this 4 oxygen to 18. So we already have 2. We cannot put anything in the front, because if I put anything in the coefficient, it will change also the number of carbon and hydrogen, and we don't want to change this thing. So just leave this oxygen, 2 oxygen atom side, and then if you have 2 oxygen atom in here, how many oxygen atom we need more to make it 18? We need 16 more, right? So if I put 8 in the front, because if I'm changing this coefficient, it's changing just the number of atom, nothing else, no carbon, no hydrogen. That's why I'm changing this oxygen atom, not the one with the C6H12O6. So 8 times 2, 16, 16, and 2 is already in here, so it's 18. So now every atom is balanced. So this is your balanced chemical equation. C6H12O6 with 8 moles of O2 gives you 6 moles of CO2 plus 6 moles of water. Let's try to do one more balancing. Let's start with nitrogen. You have 1 nitrogen, you have 2 nitrogen on the product side, so put 2 in the front. And now nitrogens are balanced. How many hydrogen now it became? 3 times 2, 6 hydrogen. There is no hydrogen in oxygen. How many hydrogen after the arrow? 2 hydrogen. So if I put 3 in the front, it becomes 6. So now nitrogen and hydrogens are balanced. Let's talk about oxygen. You have 2 oxygen atom in there. How many oxygen atom in this product side? There is no in nitrogen. You have 3 oxygen atom in water. So now there is a problem. You have 2 oxygen and 3 oxygen. Is there any number I multiply by 2 to get 3? Yes, if I multiply this number by 1.5, then 2 times 1.5 is 3, right? So now everything is balanced. But now the question is, again, you have a decimal number in the balanced chemical equation, and you cannot leave the balance in a decimal form. So you have to multiply this number with some number that can convert a decimal number into a whole number. So the smallest number. So the smallest one that we can think of is 2. and then multiply 2 with every coefficient in the chemical equation. So the final answer will become 2 times 2 4, 1.5 times 2 3, this is 1, nothing is written, so 2 and 2 plus 3 times 2 6 S2O. And if you can see one more time, now every atom is balanced. You have 4 nitrogen, you have 2 times 2 4 nitrogen, you have 12 hydrogen, 3 times 4 6 times 2 12 hydrogen are balanced. What about oxygen? 2 times 3 6 oxygen, you have 1 times 6 oxygen. So each and every type of atoms are balanced before and after the reaction. So that means this is a balanced chemical equation, right? And it follows the law of conservation of mass. So now we already learned how to calculate or how to balance a chemical equation. So now we're going to talk about the stoichiometry calculation from a balanced chemical equation. So what is stoichiometry calculation? It normally tells you to calculate the maximum number of moles of product that you can form from a given amount of moles of reactant, or the maximum mass of a product that you can get from a given mass of the reactant. For example, if you have any reaction going on, let's take a reaction. Again, H2 plus O2 gives you water, and then if this reaction is not balanced, we have to balance it. So we have 2 2, then if I put 2 in the front and then 2 in the front, now this equation is balanced. You have each type of atom. So what is stoichiometric calculation is, that means if I give you, for example, if I have 3 moles of oxygen, right, how many moles of water you can produce as a product, right? From the given equation, I can say when 2 moles of hydrogen reacting with 1 mole of oxygen, you are getting 2 moles of water as a product. But if I give you a different number than 1 mole, if I give you 3 moles of oxygen, now you have to tell me how many moles of product, which is water, you can produce. So this is a type of stoichiometric calculation, right? Or a second type of thing we can solve using a stoichiometric calculation is, if I give you a grams, let's say if I have 5 grams of oxygen, how many grams of product you can produce. So whenever we use a balanced chemical equation to solve this kind of problems or questions, we have to use a stoichiometric calculation, right? So we're gonna learn how we can solve this kind of problem in the next slide. So let's go to the next slide, and then we're gonna use a stoichiometric calculation. So the first way of stoichiometric calculation is mole to mole stoichiometric calculation. Means when the moles is given, then you have to tell me how many moles of the product you can get, right? Or how many moles of the other substance you can get. So for example, if this is the reaction going on, say O react with O2 gives you CO2 and water, and the equation are already balanced with the coefficient. If you can see over here, this is a balanced chemical equation. So from this equation, I can say we are reacting 1 mole of ethanol with 3 moles of oxygen to give 2 moles of carbon dioxide and 3 moles of water. So that means this is the ratio. If you react 1 mole of the ethanol with 3 moles of oxygen, you will always get 2 moles of carbon dioxide and 3 moles of water, right? So this is how you can get information from the balanced chemical equation, right? The other thing that you can get from here, let's go to the next slide, and then you will understand how you can use this balanced chemical equation to write the equivalency and conversion factor that you can use to solve the problem. So it's the same. So let's try to solve the problem over here, that's mole to mole. The problem saying how many moles of oxygen are needed to react with 5 moles of ethanol, right? So from the balanced chemical equation, what we know that every 1 mole of the ethanol react with 3 moles of oxygen, right? But the question is asking, if you have, instead of 1 mole, if I give you a 5 moles of ethanol, then how many moles of oxygen are required? That you need to calculate. So always remember, whenever the balanced chemical equation are given, you always write something like this. You always write 1 mole of the reactant equal 3 moles of oxygen equal 2 moles of carbon dioxide equal 3 moles of water. So they are equal. So this equal sign is saying, to make this equation work, you have to like mix certain amount to get the certain amount, right? And now look for the problem. Which thing is given and which thing is being asked? You have to just look for those two things and then ignore other two things. So what I means, the question is saying, if you have 5 moles of ethanol, how many moles of oxygen? So the given moles is ethanol, and how many moles of oxygen are required? Is there anything said about the carbon dioxide and water in this problem? No. So for this particular problem, we can ignore this thing. We don't need to worry about these two things just for this problem. And then what's left? 1 mole of ethanol equal to 3 moles of oxygen, right? And then this become an equivalency, and we can use this equivalency to make a conversion factor, and using a conversion factor we can easily calculate. So we need moles of oxygen, so moles of oxygen has to be the top over 1 mole of ethanol, C2H6O. And once we use this conversion factor, multiply this one with your given number, which is 5. So that's why we use this conversion factor over here. 3 moles of oxygen over 1 mole of ethanol, multiply with your given number, 5 moles of ethanol. Ethanol gone, you get 15 moles of oxygen. So this is how you normally solve a problem on balanced chemical equation. Okay. So let's try to do one more problem on this, and then this will help you to understand much better, right? Okay, so it's the same reaction that we used in the previous part, but now the problem is different. It says how many moles of carbon dioxide are produced. So that means you have to tell me how many moles of carbon dioxide you can produce if you react 5 moles of ethanol. So again, from this chemical equation I can say 1 mole of ethanol, C2H6O, equal 3 moles of oxygen equal 2 moles of carbon dioxide equal 3 moles of water, right? So what is given? 5 moles of ethanol. So we're gonna use this thing. We're gonna use this equation, and what is being asked? How many moles of carbon dioxide? Moles of carbon dioxide. Is there anything given for oxygen and water? No, so we don't need to use this thing. And what's left? 1 mole of ethanol equal to 2 moles of carbon dioxide. That's the only thing left. And from here I can make a conversion factor, because this is equivalency. We need how many moles of carbon dioxide? So moles of carbon dioxide has to be top, 2 moles of carbon dioxide, which is here, and moles of ethanol on the bottom, right? And multiply with your given number, which is 5 mole of ethanol. So you're gonna get 10 moles of carbon dioxide as a product if you use 5 moles instead of 1 mole that is given in the chemical reaction, right? So I would recommend always write this kind of thing, and that's ignore the thing that is not given or is not being asking for. Just focus on the thing that is being given and what's being asking for, and equate those two moles, right? And then from there you can make a conversion factor and then use that conversion factor to solve for your problem, right? Okay, let's do one more problem on this. The problem is saying, what's the maximum number of moles of carbon dioxide you can produce when you react 6 moles of glucose? And this is the balanced chemical equation. So what is given? Moles of glucose are given, okay, and then what is been asking? How many maximum number of moles of carbon dioxide? This has been asking. Is there any other thing given for oxygen? No. Is there anything given for water or any information for water? No. So we usually don't care about this equation, this moles for this problem. What is left? The equation is left is 1 mole of glucose giving you 6 moles of carbon dioxide, and I can use this equivalency to make a conversion factor, right? So it says maximum number of moles of carbon dioxide, so carbon dioxide has to be on the top, moles of glucose on the bottom, and multiply with your given number. 6 moles of glucose cancel. When you multiply, you will get the number of carbon dioxide that you can produce with the 6 moles of glucose, right? So this is how you can do this kind of problem, right? Let's do one more problem on this. So this is the balanced chemical equation which is already given for you, and it's saying using this equation you have to solve the problem. It says how many moles of HCl are required to react with 5.60 moles of magnesium, right? So what is given? Magnesium is given. What you need to calculate? How many moles of hydrochloric acid? Is there anything given for magnesium chloride and hydrogen gas? No. So we can ignore this thing, and from these two thing that is given and been asking, I can say 1 mole of magnesium from the balanced chemical equation react with 2 moles of HCl, right? And then we can equate these two things, and then from here I can make a conversion factor, and we need moles of HCl. Moles of HCl has to be on the top. This is hydrogen chloride, not hydrogen chloride, right? So moles of magnesium get cancelled, and 2 moles of hydrogen chloride multiply with 5.60, you will get 11.2. So yeah, so make sure you practice this kind of problem and try to make a equivalency. So always make an equivalency which is given and which is asking between these two, and then ignore all other thing. Okay, so on the previous topic we just learned from a balanced chemical equation how you can get the number of moles of the required thing if the number of moles is given. So that means we just learned from mole to mole conversion using a balanced chemical equation. But if instead of moles, if the mass of the one of the reactant is given or one of the substance is given, and then it's been asking how many grams of the second substance you can get using a balanced chemical equation, then we're gonna learn how we can solve this kind of problem. For example, again H2 plus O2, for example, right, gives you water. This is 2. This is a balanced chemical equation. For example, if I say I used 5 grams of oxygen, how many grams of water you can produce? So that means this is mass to mass stoichiometric calculation using this chemical equation. You have to tell me how many grams of oxygen from, if you mix 5 grams of oxygen, right? So we're gonna try to learn this kind of problem, right, and then try to solve it. So the main concept in here is, if the mass is given, convert that mass into a mole of that substance first, and from the chemical equation connect how that moles of one substance connect to the moles of the second substance that is being required. And once you get the moles, you can easily get the mass of that substance, right? So remember this thing, this is the most important thing, moles and moles, and it always comes from the chemical equation, right? So we're gonna do some problem that will help you to understand much better than just seeing this formula. So let's get to the next slide and then try to convert a mass to mass or use mass to mass stoichiometric calculation. So there are a couple of steps that you need to use, you can read this step and then apply the concept that we're gonna use in the next problem, right? So I'll directly explain you on the problem by itself how you're going to use this concept that is written over here to solve the problem. So let's get to the next slide. Okay, so now let's try to solve this problem and understand mass to mass conversion using a balanced chemical equation. So the problem is saying what mass of nitrogen is produced. So that means it's asking how many grams of nitrogen you can produce when 130 grams of sodium azide. How many grams of sodium azide that is given? 130 grams of this reactant. Decompose in air bag. Whenever you decompose 130 grams of sodium azide, how many grams of nitrogen you can get? So this is a problem, a question that you need to solve for. So let's take a solution map or boxes. So what is given, you have to write that thing first. We have mass of NaN3 sodium azide, that is given. What I can get from mass of sodium azide? I can get moles of sodium azide, Na3, and once I get the moles of Na3, is there any way I can get the moles of N2? Right, we are ignoring sodium in this reaction because nothing is being given, nothing is being asked, so we ignore this sodium for this reaction. So our focus is between Na3 and nitrogen. So to get the grams of nitrogen gas, what we need to have before I can convert to the grams, we need to have moles of nitrogen. Then I can use the rule that convert moles of nitrogen to the mass of nitrogen. Right, so now let's see how they are connected, how the first two boxes are connected, mass of Na3 to moles of Na3. By rule, I can say 1 mole of Na3 sodium azide is equal. So the thing is that we need to put 1 mole on the top because the arrow is going from mass to mole, so mole has to be on the top. Na3 sodium azide is equal to 65.02 grams of sodium azide, Na3. And I hope that you know why I got 65.02, because I added sodium atomic mass and 3 atom mass of nitrogen, right? So this is how you can get the combined mass, and this is by the rule. How the other two boxes are related, moles of Na3 and moles of N2. So there is no rule given in this chapter that connect the moles of N3 to another moles. So there is no other way beside the chemical equation. So I can say, using a balanced chemical equation, I can say 2 moles of Na sodium azide giving you 3 moles of nitrogen gas. This is the ratio between the two thing in the chemical reaction. So we need moles of N2. So moles of N2 has to be the top. 3 moles of N2 coming from every 2 moles of Na3. And once we get the moles of N2, how we can get the mass of N2? So we need mass has to be on the top, moles. So I can say if I have 1 mole of N2, how many grams of N2? The molar mass of N2. Because each atom of nitrogen is 14.01, you have 2 atoms of nitrogen, so combine both the nitrogen atomic weight, you will get 28.02. So now you have everything. Multiply these conversion factor with themselves and along with your given number, which is 130 grams of sodium azide, Na3. Now let's say grams of Na3 cancel with grams, moles of sodium azide, moles of sodium azide, moles of N2, moles of N2. Then what's you left with? Grams of N2, right? And that's what we needed, grams of N2. So your final answer is gonna be around 84 grams of N2. And we started with 2 sig fig number 130, you end with 2 sig fig number 84 grams. So this is how you solve the problem, from mass to mass, right? So let's try to do one more problem on this so you can understand better. Let's do one more. So this is a new problem that's been asking about how many grams of oxygen are needed to convert 12 grams of ethanol into product. So the question is saying, if you have 12.0 grams of ethanol, how many grams of oxygen that you need, so that if they react with 12.0 grams of ethanol, when they react, everything is gonna combine and then convert into a product. So how many minimum amount of oxygen that you needed to react with 12.0 grams, right? So again, this is a problem from mass to mass conversion. So let's start with the first one. First box, what is given? The given thing is mass of ethanol. If I have the mass of ethanol, what I can get? I can get moles of ethanol. If I get the moles of ethanol, which thing I can get if I have the moles of ethanol? I need grams of oxygen, so I need to have some way moles of oxygen, because only from moles of oxygen I can get grams of oxygen. So is there any way I can get moles of oxygen from moles of ethanol? Yes, from the balanced chemical equation. The equation is, so nothing is given between carbon dioxide and water, we are ignoring this thing. So our equation will be between ethanol and oxygen. I can say every 1 mole of ethanol reacting with 3 moles of oxygen, right? So I can get moles of oxygen from this two relation. And once I get the moles of oxygen, I can get mass of oxygen. Right? So let's take a conversion factor, how the first two boxes are related. Moles of ethanol. I can say 1 mole of ethanol is equal to how many grams? I can say 46.07 grams of ethanol, because you have to add atomic mass of 2 carbon, atomic mass of 6 hydrogen, and atomic mass of 1 hydrogen. When you combine each of them together, you will get 46.07 grams, right? Let's talk about the other two boxes, how these two boxes are related. Moles of ethanol, moles of oxygen. From the equation, I can say I can get 3 moles of oxygen, right? This is 3 moles. If I react 1 mole of ethanol, right? This is the balance equation is saying something like this. So this is how you connect. And once I get the moles of oxygen, I can get the mass. So by rule, I can say 1 mole of oxygen is equal to 32.00 grams of oxygen. Once you have all the conversion factor, multiply, right? Multiply with your given number of ethanol, which is 12.0 grams of ethanol. So ethanol gone, moles of ethanol, moles of ethanol, moles of oxygen, moles of oxygen. And what's left? Grams of oxygen. So once you solve everything, you end up with 25.0 grams of oxygen. So this is the amount of oxygen that you needed to react with 12 grams of ethanol, so that once the reaction is done, nothing is left of the reactant side, everything converted into a carbon dioxide and water. So this is your answer for this problem. So one more thing before we finish this problem, make sure you know how to calculate the mass of 1 mole of oxygen, right? Each atom of oxygen is 16 gram. You have 2 atoms, so that's why you have 32 grams, right? So this is how you normally solve this kind of problem. Okay, so now on this slide we're going to talk about what are the different type of chemical reaction in chemistry. So there are many different types of chemical reaction in chemistry, but to better understand so many reaction, chemists normally use to divide all those type of reaction in basically 4 broader categories. So the first one is combustion reaction, second one is decomposition, third one is single replacement, or you can also call as single displacement, or double replacement, or you can say double displacement. Double displacement reaction, right? I'm gonna talk about each four of them, right, separately. And we have some other classification also that include oxidation reduction reaction, acid and base, combustion, and some reaction involving organic compound. So we can, in this class we're going to talk about the oxidation reduction from this classification, and then we're going to, when we talk about acid and base chapter, then we're going to talk about acid and base. So let's talk about these 4 reaction first: combustion, decomposition, single replacement or displacement, double replacement or double displacement reaction, right? And let's talk about each of them separately. So the first one we're going to talk about is combination reaction. As the name is already telling you about this thing, when 2 or more atoms combine together to make one product, we call them as combination reaction. For example, let's say if any random element A react with B, they combine together and make a single product AB. This is your combination reaction. So the concept is 2 reactants combined to form a single product, right? Let's take a couple of examples on the next slide. So these are some of the example of combination reaction. N2 nitrogen gas react with oxygen gas, giving you nitrogen monoxide, right? Sodium react with chlorine gas, gives you sodium chloride, one single product. So this is a type of combination reaction example. Let's talk about the second type of reaction, decomposition reaction. As the name is again already telling you about this type of reaction. Decomposition means when a single compound decompose or break down into 2 or more elements or compound, right? Basically one reactant split into 2 or more product, right? For example, this is a random element or compound AB. When you split them, it's gonna split into A and B. So this is a decomposition reaction. So we're gonna take some example on the next slide about the decomposition reaction. So these are the example of decomposition reaction. Sodium azide, when it decomposes, give you nitrogen atom, sodium atom and nitrogen gas. Carbonic acid, H2CO3, when you decompose it, you will get water and carbon dioxide, 2 products from a single reactant, right? Okay, so let's go to the next. So this is the third type of chemical reaction called single replacement, or we already talk about this thing, or we can call as single displacement reaction. So in this single replacement or a displacement reaction, an element substitute for an atom in a compound to produce a new compound, a new element. What does it mean? Let's say if this is an element, before the reaction is separate, when react with a compound B and C, it will replace B from its compound and take the place of B, and then move the B separate. So if you can see in the products are now A belongs to C to make a compound and B is left alone as a single entity. So that's why the name is single displacement. You are replacing one single atom at a time with the other atom, right? So let's take an example on the next slide for this single replacement reaction. So this is an example of single replacement reaction where magnesium in solid form react with hydrochloric acid, is in aqueous, dissolve in water, gives you product magnesium chloride and hydrogen gas. So what's happening in over here, magnesium is replacing hydrogen from the compound hydrochloric acid, and hydrogen is coming out in the form of a gas, hydrogen gas. So that means you are replacing one element at a time, right, to make magnesium chloride and hydrogen gas. And if you can see on the picture on the left hand side, you see a magnesium metal and you see some bubble coming out. This bubble is your hydrogen gas, and this is a proof that the reaction is happening because you are bubbling up hydrogen gas. Right. Then the last reaction is a double displacement reaction or double replacement reaction, where you are replacing or two atoms at a time. So for example, on the given example that is given over here, in a compound A, B and C, D, A will replace C and C is going to replace A, right? And you will get AD and CB. That means two atoms are going to replace each other in a different compound to form a new compound as a product. So that's why the name is double displacement reaction. So this is an example of a double displacement reaction where potassium iodide react with lead nitride, gives you potassium nitrate and lead iodide, right? So what's happening over here, potassium is taking the place of lead and lead is taking the place of potassium. That's why lead nitride is going to form and potassium iodide or lead iodide is going to form, right? Similarly, in the second example, sodium hydroxide react with hydrochloric acid to give you water and NaCl. What's happening in here, sodium is going to replace hydrogen, hydrogen going to replace sodium. That's why you're going to make water and NaCl. So this is also an example of double displacement reaction. So now let's talk about a different type of reaction, a new type of reaction called oxidation reduction reaction. And we call this oxidation reduction reaction as a redox reaction, where Re comes from reduction, Red comes from the reduction, and OX comes from oxidation, redox reaction, right? And where you can use this type of reaction, this reaction we can use in energy producing reaction in a cell, like cellular respiration, as an internal combustion engine, in a batteries, hydrogen fuel. So we have multiple uses of this redox reaction. So let's understand what is redox reaction, oxidation and reduction reaction. So oxidation reduction reaction is a type of reaction where you can transfer the electron, right? So oxidation is a reaction where the element loses electron or donate electron, you can say. And reduction is a process or a reaction where you gain electron or accept electron that is being donated by the oxidation, right? So oxidation reduction reaction always occur together. There is no way you can get the reduction reaction but there is no oxidation reaction, right? So there is a trick to remember this definition of oxidation reaction. You can use oil means oxidation is loss. So that means whenever you're losing an electron, that means you're doing oxidation. If you have to remember reduction, you can use the term RIG. That means reduction is gain of electron, when you gain an electron. So this will help you to just remember the definition. But always remember oxidation, loss of electron, or donation of electron, reduction, gain of electron, right? So let's take an example of this reaction on the next slide. So this is an example going on. AgCl react with copper, gives you copper chloride and silver. So what's happening in here, if you see before the reaction, what's the charge on silver? This entire molecule, the charge on this silver is +1. This is ionic compound because chlorine is -1, so silver has to have +1 charge, right? Copper don't have any charge because this is present in solid form, no charge. after the reaction, this is also an ionic compound, copper chloride. Copper has to have +2 charge to neutralize the chloride ion, right? And silver after the reaction doesn't have any charge, 0 charge, because this is present in solid form, no charge. So what's happening in this reaction? So we can say before the reaction silver had +1, after the reaction silver had no charge. So how is it possible? There is only one way it possible. If silver is going to take an electron from somewhere, one electron, to neutralize this one positive charge on silver, right? So that means silver is doing a reduction reaction because it's going from +1 to 0 charge by taking one electron, right? What about copper, an element? Before the reaction the charge on copper is 0. After the reaction, was the charge on copper in a compound? +2. How is it possible to get it 0 to 2? That means it donates 2 electrons. It donates 2 electrons. That's why in ionic compound, whoever donate electron get a positive charge. So that means copper is doing oxidation reaction, right? And then we can make two separate reaction from this chemical equation that is given on the top. So the first reaction for oxidation, you start with copper, no charge, and once the reaction is done, you will get copper +2 by donation of 2 electron. Now the 2 electron is left the copper. And silver need how many electron? Silver is going to take the electron, but copper is giving up 2 electron. So and each silver need 1 electron. Then how many silver it need? 2 silver, right, to use all the 2 electron. So if you can see, these 2 electron that is donated by copper to do oxidation reaction is being used by the silver ion to do the reduction reaction. So that's the reason oxidation reduction reaction are always occur at the same time, because the electron given out by one element is going to use by the second element, right, to do the oxidation reduction reaction, right? Okay, let's take an example of sodium chloride, reaction of sodium with chlorine in the form of oxidation reaction. So this is the reaction, NaCl2 gives you NaCl, right? What's the charge on sodium before the reaction? No charge. What's the charge on chlorine? Is a gas, right? No charge, because it's a diatomic molecule, no charge. Now once they react and made a molecule NaCl, what's the charge on sodium? +1. What's the charge on chlorine? -1. So now they get charged. So we have two reactions going on. Sodium is converting into a Na+, so that means sodium is doing oxidation reaction because it losing the electron, is donating the electron, right, to a chlorine. That's why chlorine is getting a negative charge by accepting the electron. So chlorine is doing reduction reaction, right? So I can write this equation something like this: Na convert into Na+, gives you 1 electron, right? And what about the chlorine? So chlorine is in the beginning is Cl2. How many electron it need? 2 electron to convert into 2 chloride ion, right? So this is your oxidation, and chlorine is accepting the electron. This is your reduction reaction, the bottom one. But now the problem is sodium is donating just 1 electron to convert into 1 positive charge, right? But how many electron chlorine need? You have each chlorine need 1 electron, right, to get stable 8 electron octet. You have 2 chlorine atoms, so that means it need 2 electron, but sodium is giving 1, so that means you have to balance it, right? So if you have 2 sodium atom, that's how you can get 2 electron, and this 2 electron is going to utilize by the chlorine gas to convert from neutral molecule to a ion form, chloride ion, right? And now you're gonna make 2 molecule of NaCl over here, 2 NaCl, right? So this is the form of oxidation reduction reaction. So till now we just learn about the oxidation reduction reaction with the help of electron. So those element which can donate electron is doing oxidation reaction, and which one is taking the electron or accepting the electron is doing reduction reaction. But there are other definition of reduction or oxidation reaction, because there is not always a transfer of electron. So oxidation can also be defined as increase in the oxygen atom or decrease in the hydrogen atom. Whenever you are doing any reaction where you're increasing the oxygen atom in a molecule or decreasing the hydrogen, you are doing oxidation, and vice versa for reduction. If you are decreasing oxygen or increasing hydrogen, reduction. So we'll take one example on this where you have different increasing or decreasing the oxygen and hydrogen, right? And we'll see how you can define oxidation and reduction. So this is the reaction of combustion of methane, where methane react with oxygen, giving you two products, CO2 and water. And we're gonna use this reaction to identify which element or compound is doing oxidation reaction or which one is doing reduction reaction. So let's go to the next slide and let's try to understand. So let's do the same reaction. Methane react with oxygen, CO2 and H2. If you can see over here, in methane, carbon attached with 4 hydrogen, but after the reaction the same carbon attached with 2 oxygen, and then you remove all the 4 hydrogen. So what's the definition of oxidation? Now carbon remove all 4 hydrogen, that means decrease in hydrogen, and now carbon has more oxygen that was not before, so increase of oxygen. So that means this is an oxidation reaction. Carbon is doing oxidation reaction. What about O2? Before the reaction you have 2 atoms of oxygen, right? After the reaction you have just 1 oxygen, that means you decrease the number of oxygen and you have 2 hydrogen atom attached to it, that means you increase the number of hydrogen. So that means this reaction is called reduction reaction. So this is how you can predict whether which element or compound is doing oxidation or a reduction reaction, depending on increasing or decreasing the number of oxygen and hydrogen atom. So make sure you practice this kind of problem, and let's go to the next slide and try to solve a couple of problems on all these concepts that we got in type of chemical reaction. So the problem is saying classify the following reaction that is given on the bottom as a combination reaction, decomposition, single displacement or double displacement reaction. So out of the 4, which one belongs to which one? So let's try to do one at a time, and then we'll try to understand why you have this particular type of reaction for name for that particular reaction. The first question is saying AgNO3 react with CbR2 gives you AgBr and calcium nitrate, right? So which kind of reaction? If you can see in the product side, bromine is attached with the silver, but before the reaction bromine was attached with calcium and nitrate attached with silver, right? And now nitrate is attached with calcium. So that means silver replaces calcium and calcium took the place of silver. So this is a double displacement reaction, right? What about the second type of reaction? Carbon react with chlorine gas gives you carbon tetrachloride, CCl4. So you have more than 2 reactant combining to form a single product. So this is an example of combination reaction, right? In the third type of reaction you have calcium carbonate giving you calcium oxide and carbon dioxide. So that means a single reactant giving you 2 product. So that means this has to be decomposition. So this is a decomposition reaction. For this kind of reaction, chlorine gas react with sodium bromine give you NaCl and Br2. What's happening over here? If you can see, sodium attached with bromine in the reactant side, but in the product side sodium react with chlorine. So that means chlorine replaces Br and Br going to left alone, right? It's gonna make its own product. So now this is a single displacement reaction where one halogen is replacing second halogens, right? So NaCl Br2. So this is a single replacement or single displacement reaction. And then this is the last problem that we're gonna do. It belongs to the oxidation reaction. So let's try to do this problem. How can you determine that is this reaction is a redox reaction? How would you know? So if you can see in the redox reaction, what happening is the transfer of electron or addition of oxygen and hydrogen. So if you can see, before the reaction was the charge on chlorine, zero charge, because this is a diatomic molecule. Second reactant, you have ionic compound, sodium is +1, iodine is bromine is -1. After the reaction, sodium is +1, chloride is -1, bromine is 0. So what's happening over here, if you can see, before the reaction happened, chlorine has 0 charge, but after the reaction, chlorine get a -1 charge, right? So that means it's a reduction reaction, because chlorine took 1 electron from somebody. That's why it got a -1 charge. But if you see bromine had -1, but after the reaction, bromine has 0 charge. That means bromine given out or donate 1 electron, right, to somebody else. And what is somebody else? Chlorine, because chlorine got that electron. So this is your oxidation reaction. And the sodium doesn't change any charge, +1, so the sodium is not doing anything. So this is a type of redox reaction where chlorine is doing the reduction reaction, bromine is doing an oxidation reaction. This is a donate electron, and reduction is accepting electron, right? So this is how you can identify whether the given reaction is a redox reaction or not, right? So I think that should be it for this chapter. Make sure you practice all the problem that we done in this PowerPoint along with reading your textbook, and then yeah, I'll see you in the next video starting a new chapter. Bye.